Okay, let's do binomial theorem. All right, so first thing I want to show you on binomial theorem, as you can see, it's given to you as Pascal's triangle. So a Pascal's triangle, this is one way to expand binomials. Um, and you've probably seen this before in the past, but it's just a good review. So first thing you notice is that each level, like for instance, this first one, the top of the triangle would represent polynomials or binomials with a degree of 0. Anything to the 0 power is 1. So that's a simple one. And then the next level would be if you had a first degree polynomial. So a binomial that would be a degree of 1. Well, then the leading coefficients would follow this pattern. All right, so the first one would be a 1 in front, and then, so the leading coefficient, sorry, would be a 1, and then the next coefficient of our next term would also be a 1. Okay, so then if you had like a quadratic, for instance, and let's say it was just a very simple quadratic, well, then that simple quadratic may have a leading coefficient of 1, say like an x squared, and then the second term, which is usually an x, would be just a plus 2x, for instance. And then our last term would have, if it was just a constant, as an example, then it'd be a 1 at the very end. Now, these can change a little bit, don't get me wrong, but these provide these multiples to help us give us an outline for our binomial expansions. So what I want to first do is just make sure you understand how Pascal's triangle works, and then we're going to apply it to some simple examples. So the first thing is, you can see I have each level, there's degree of 0, the second tier right here is degree of 1, and then it goes down right here to the third one, which is degree 2, and it keeps on going. I have 7 listed. And what I want you to notice first of all is a pattern. On the outsides right here, on the sides of the triangles, notice they're all 1s. Right? On our triangle, all of them are 1s. And then what's happening that's important is what's happening in the interior. So the first one's 1, the next level is 1 and 1. It's this third level where you start seeing something interesting. So 1 and 1 are on the outsides like we talked about earlier, but on the inside is now a 2. And the way we get that 2 is we take the level above it, the 2 squares we were dealing with, the rectangles, whatever you want to say, is that we take 1 and 1 and we add those together and we get the 2, which is how we get that leading coefficient for the term on our, in this case, quadratic polynomial. And then for the next level, the ones on the outsides again, and then this 3, we get it by adding 1 and 2 to get 3. And then this next 3, we get it by adding 2 and 1 to get that 3. And then you can see the next level is the same thing. 1's on the outsides. Well, 1 and 3 gives us 4. 3 and 3 gives us 6. 3 and 1 gives us 4. And then, as we talked about earlier, 1 on the outside. So that continues. So it's a nice little, I guess you can call it a trick, but Pascal's triangle helps us set up these problems. The only downside about it is you have to go and set Pascal's triangle up all the time over to the side if you want to use it. And so we'll talk about another way of doing these problems. But before I get to that, let's use Pascal's triangle with a couple examples. So the very first one we have is x plus y squared. And I want to show you first, just the way you've always done this problem, is you just multiply x plus y times x plus y, which when you distribute just becomes x squared plus xy plus xy plus y squared. So you can see we would get, well, 1x squared plus 2xy plus 1y squared. If you look back at Pascal's triangle and pay attention to the coefficients listed, you'll notice there's that 1, 2, and 1 that's on Pascal's triangle for the quadratics for the degree of 2. So we can continue with this idea and say we had x plus y cubed. Well, x plus y cubed would be x plus y times, well, we just now did it, x plus y squared. X squared plus 2xy plus y squared. Okay, and if we took x and distributed it all the way through, there's your x cubed plus 2x squared y plus xy squared. Now we're going to distribute our y, so x squared y plus 2xy squared plus y cubed. So when we combine like terms, we have x cubed plus 3x squared y plus 3xy squared plus our y cubed. Okay, so once again, if you look at that third degree on Pascal's triangle, I didn't write them in there this time, so let me go and squeeze it in real quick. You'll see that we have our 1, 3, 3, 1. So if we're looking at our last one right here on example 1, it's part C. It's saying, what is x plus y to the fourth? So instead of doing that expansion again, where we're having to multiply everything through with distribution, we could just use Pascal's triangle to help us out. Okay, so looking back at Pascal's triangle, first of all, you notice that for the fourth degree, it's going to follow the pattern of 1, 4, 6, 4, 1. All right, so we know this is going to provide kind of an outline for us. Now, if we look back and notice some patterns here, it looks like when we have two variables, an x and a y, we had x squared, then it became x to the first, and then we didn't have an x. Or you can just think of that basically being like an x to the 0 right in there. So this was an x to the 0. Well, what's x to the 0? It's 1. So we didn't have to write that in there. Okay, so that makes sense. Look at it happens on part B as well. X to the third, x to the second, x to the first, x to the 0, which we don't have to write in there because x to the 0 is 1. Well, now, how are we working with the y's then? So it looks like their exponents on the x's are decreasing by 1 as we go from one term to the next. But when we look at the y's, this would be y to the 0, right? Because y to the 0 is 1. Y to the first, y to the second. Look at the part B, y to the 0, y to the first, y to the second, y to the third. So it looks like as the x exponents decrease by 1 each time, our y exponents increase by 1 each time. Okay, so let's use that idea here. So we know we're going to have 1, okay, because this is the 1 at the very beginning, x to the fourth, y to the 0. Okay, and now we're going to say, okay, the next one's 4, so 4, x to the third, because remember our x's always go down 1, y to the first, because our y's always go up by 1. And we'll continue. 6, x to the second, y to the second. 4, x to the first, y to the third. 1, x to the 0, y to the fourth. So these y to the 0, this y to the 0 and this x to 0 are just 1s. And so just to kind of write it a little bit cleaner, it'd be x to the fourth plus, what is that, 4x cubed y plus 6x squared y squared plus 4x y to the third. Finish off with y to the fourth. All right, example 2. We're going to talk about what a combination is. First of all, this notation. You're going to have a number here for n and a number here for r, and the C just represents what's called a combination. Now, another way of writing it is to just write these parentheses, and then you have your n and you have your r. You're going to see me write it like that more often than not, just because that's what I have in my past. And the words you hear me say are n, choose, r. That's kind of the, when I see an n and an r, you'll see me say, well, that's, like for instance, part A, that's 9, choose 2. That's what you hear me say. Okay, what we do is we take the values that we have and we substitute them in this formula and we crank those out. All right, so you have n factorial over n minus r factorial quantity, n minus r factorial, times r factorial in the denominator. So all that stuff. So let me go about it, and I'm going to show you a shortcut after this. So remember, this would be the same thing as parentheses with a 9 and a 2, and we're going to say it's 9 choose 2. So just using the formula, we have 9 factorial over 9 minus 2 factorial, 2 factorial. I'll put in parentheses so you can see them all a little easier. Okay, so you can see that there's our n factorial, n minus r factorial, and our r factorial, just going straight from the formula. Well, that's the same thing as saying just 9 factorial over 7 factorial times 2 factorial. Okay, we've done this in the past, but it'll be good to see it again. 9 factorial, remember, is 9 times 8 all the way down to 1. 7 factorial, do the exact same thing. All right, put that in parentheses. And then we have our 2 factorial. Well, if we were to take this back half right here, back portion rather, of our numerator that I put in parentheses, well, that right there is the exact same thing as this set of parentheses in the denominator. That's 7 factorial. So all of those would simplify to become a 1. So the only thing we're left with is 9 times 8 over 2 times 1, not 2 times 4, 2 times 1. Sorry about that. 9 times 8 over 2 times 1. Let's just fix that. There we go. Which is 36. All right, so that's cool. So that's what a combination is. Now, I don't typically think of it that way. So let me show you the way I think about when I see 9 choose 2. When I have this, I actually don't do any of these steps right here. I skip from here all the way to there. And so I'm hoping that you like the way I'm about to teach this, because you can see we eliminate quite a bit of work, and we can just go from here straight to this fraction and then simplify, and we're done. So here's how I think about 9 choose 2. If I were to give, I'm coming with a margin. Hopefully that'll be good enough. So 9 choose 2. What I do is I take the first number, or the number we're working with, 9 obviously. I go ahead and write that down. And then I keep on multiplying the factorial out until I have written 2 numbers down, because there's a 2 right here. So I would say 9, and I would go, okay, that's 1 number, so that's not enough. Now I say 9 times 8. Well, now I have 2 numbers now written in my numerator. If that was a 3, for instance, then it would be 9 times 8 times 7. If it was a 4 right there instead of a 2, it would be 9 times 8 times 7 times 6. So hopefully you see the pattern. Well, since I have 2 numbers listed, I'm done. So then in the denominator, it's just whatever this number is right here, the r value, or 2 in this case, you just go ahead and do 2 factorial in the bottom. So over 2 times 1, which is 36. So you can see this is significantly shorter, and that's just the way I'm thinking about it. If you would rather do this longer process, that's fine. If you like this, the more you practice it, the better you'll get at it, and you'll finish these problems considerably faster. And I'm going to come back to this thought, but let me go ahead and just do a couple examples with that thought process first. So 11 choose 4. So that'd be 11 times 10 times 9 times 8. We've now written 4 numbers, which is what's in this bottom part of our combination. So we were done. So now we just go divided by the factorial, 4 factorial. I like to simplify by just saying, well, 4 times 2 is 8, so that would simplify. The 3 and the 9 would become a 3, so it's just 11 times 10 times 3, that'd be 330. All right, so the next one is, I'm going to show this one. This one I had memorized, and you'll see it's pretty easy to memorize. We're going to use it a lot. But let me do this one real quick, just using the old school rule right here of a combination. So n factorial, so 8 factorial over n minus r, so 8 minus 0 factorial times 0 factorial. Well, you can already see it. That's 8 factorial over 8 factorial, 0 factorial. Well, the 8 factorials would simplify to 1s. And then 0 factorial is 1. So you have 1 over 1 times 1, which is 1. So anything right here, if you have a number and you say, well, 8 choose 0, 7 choose 0, 3 choose 0, whatever it is, that's always going to give us 1 as an answer. So hopefully that helps a little bit with combinations. The more we practice them, you're going to see me doing quite a few of these. I think it'll help out. Now I want to make one little side note, and this is going to be helpful for us. Okay, so one thing you'll notice as you work these, and I'll just take, I'm going to go back to you know what? I think it's better if you work these out. You'll see the pattern rather than me just try to describe. Because I was going to go here as I'm going to show you why a certain thing works. But I think as you do them, you'll see it. So let's just look at part B, for instance. 11 choose 4. 11 choose 4 is the same thing as 11 choose 7. So you already know 11 choose 4 is 330. If you go off to the side and you work that problem out, 11 choose 7, you're going to get 330 again. So 11 choose 4 is 330, so is 11 choose 7. All right, so let me look at this with part C one right here. 8 choose 0, we know is 1. We just did it. Well, I'll tell you also that 8 choose 8 is also 1. If you go off the side, you'll see, well, yeah, it's 8 factorial over 0 factorial times 8 factorial. Basically the exact same thing division we did right here. Or it's 8 choose 8. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all divided by 8 factorial, which is 1. So these are the same. These are the same. And you might see a pattern here. I'm not sure, but just in case, I'll go ahead and write one more. Squeeze it in here on this last part. 9 choose 2, the one we were working with on the very first problem. I'm going to tell you the exact same thing as 9 choose 7. And I'm hoping that if you worked all three of these, 9 choose 7, 11 choose 7, and 8 choose 8, that you'll see that they're the exact same answers as the one we did before. And here's the reason why. Well, here's a shortcut to it, rather. 9 minus 2 is 7, just like 9 minus 7 is 2. 11 minus 4 is 7, just like 11 minus 7 is 4. 8 minus 0 is 8, just like 8 minus 8 is 0. So that's kind of the way that a trick of you figuring out what combinations are the same. Now, why does that work? It all goes back to this rule, and you can just see just which order do you simplify in. And if you look back at that, you'll see that it connects pretty quickly. If that's not good enough, that's fine. Come with me to tutorials, and I'll explain to you very, very concisely. I think you'll get it fairly quickly. But just understanding that these are equivalent is going to help us with what we're doing today. So I want to go ahead and mention it at that point. All right, let's try to do some examples of these now. All right, so the very first one, a plus b to the sixth. So one way you can do is Pascal's triangle, which is nice. It'll list it all out. But remember, you'd have to go and make Pascal's triangle off to the side of your own if you're not given it, which can be quite irritating. And obviously, as this degree gets larger, that becomes even more of an issue with Pascal's triangle. Furthermore, if I were to show you some application problems, which I'm probably going to make a video for just because I think it's important to see, you're going to see that the use of how the method I'm about to show you right now, the binomial theorem, is, in my opinion, much better. But let's just dive right into them. So if you had a plus b to the sixth, and we're trying to expand that out, you take this number 6, and that's what's always going to be at the top of your combination. So we always have our 6's right there. All right, and the very first one we're going to do is always we're going to say 6 choose 0. All right, then you have 2 more sets of parentheses. All right, and these are the spots from your binomial. That's what you put in those positions. So right now, A is in the first position in our binomial. So I'm going to put the A right here in that set of parentheses, just to keep things organized. And then do the same thing with the B. I'm going to put it right there. It's a plus B, so I'm going to have a B. Okay, and then remember what we did earlier with our x's and y's when we had our x plus y squared and x plus y cubed that we did in example 1. This number is going to start way up here at 6, and it's going to start to count down. And then this b, remember, is going to start at 0, and it's going to be counting up. Its exponents are going to be counting up. So we just keep on listing these. So now we have plus. We'll go 6 choose 1. We have 2 sets of parentheses, one for the a and one for the b. Remember, a is going to go down 1, and b, its exponent's going to go up 1. All right. So then the next one. 6 choose 2. We're going to have a spot for the a and a spot for the b. So the a is a 4 and the b is a 2. Okay, continuing on, we would now have 6 choose 3, a and b. So remember, our a is going down by 1, B's up by 1, so 3 and 3. Then 6 choose 2. A squared, b to the 4th. 6 choose 1. I'm sorry, 6 choose 4. There we go. I knew something wasn't right there. 6 choose 4. All right, and now 6 choose 5. A to the 1st, b to the 5th. And I thought I was going to be able to. I can't, so I'm going to have to go one more step down here. 6 choose 6. A to the 0, b to the 6th. Okay, so I want to list all those out and then just talk about them first. Okay, I'm going to try to do I'm going to try to give you just a quick little review over all this in this one problem. Because example 3 has like 5 parts, I'm not going to do all those parts. So I'm going to try to give you just an instructional part on this. First of all, notice that we start with 6 every single time in our combinations. It's always the top number. Okay, notice that we started with 6 choose 0, and then it increased by 1 each time. So it became a 1, then a 2, 3, then a 4, 5, and a 6. All right, so we had all those worked out. And now look at our A's. They went from a 6 to a 5. It counted down. We've talked about that several times now. And the B's were increasing. So some good pattern recognition here that's going to help you with organizing this is that this number at the bottom of our combination is always going to match our second quantity, our B in this particular example, its exponent. So notice right here on this term, it was a 1, and the exponent on our B is also a 1, and it continued all the way through, a 2 and a 2, a 3 and a 3, 4, 4, 5, 5, and then of course our last term had 6s. And the other thing I'm going to talk about is that you notice that these exponents are 6 and are 0. Well, their sum is equal to 6. 5 and 1, its sum is equal to 6. 4 and 2 is equal to 6. And so on and so forth. 3 and 3 equals the top number of the combination, 6. 2 and 4 is equal to 6. And it works for each term. And that's because we're dealing with a 6-degree polynomial. So they're all going to be degrees of 6. Okay, for binomial expansions. So that's the setup. And that's good patterns to kind of help you out with your setups. Now let's do some computation with them. Remember, anything choose 0 is just a 1. So this very first term, that 6 choose 0 is going to become a 1. Now we're going to work with 6 choose 1. Let me come over to the side so you can kind of see how it's worked out. So remember, I write down 6. And I'm going to continue writing numbers until I have one number written. Well, that's happened already. That's the 6. And we're going to divide that by 1 factorial. Well, 1 factorial is just 1. So basically 6 divided by 1. Therefore, that combination is equal to 6. Do the same thing right here for 6 choose 2. 6, we're going to write 6 times 5. Well, now we've written 2 numbers, because that's what we're supposed to write, 2 numbers, over 2 factorial. So over 2 times 1. 6 times 5 divided by 2 times 1 is 15. All right, now we're on 6 choose 3. So 6 choose 3, it would be 6 times 5 times 4. We now have 3 numbers written, all over 3 factorial. Well, 3 times 2 is 6, so those 6's would simplify to make 1. So basically it's just 5 times 4 divided by 1. So that one's 20. And I'll do one more right here. And it's 6 choose 4. I want that to throw you off. I'm just going here to the side or here below. Okay, so that would be 6 times 5 times 4 times 3, all over 4 factorial. All right, well, the 4 times 3's would simplify. Okay, and here's what I want you to notice. So we talked about this earlier. We've already done this. 6 times 5 and 2 times 1 is what we have left over. Well, that's the same thing as this one up here. 6 times 5 divided by 2 times 1, which we know the answer is 15. So I'm going to go ahead and write that. but it goes back to what we were talking about earlier with combinations. 6 minus 4 is 2. Therefore, it's going to be equal to the combination of 6 choose 2, just like 6 minus 2 is 4. So we talked about this. 6 choose 2 and 6 choose 4 are equivalent. That's why we both get 15, no matter how we do the problem. Well, therefore, 6 choose 5, you can do it you can go about and do it this way right here, but isn't 6 minus 5 1? We already know that 6 choose 1 is 6. Therefore, 6 choose 5 is also going to be 6. And the last one, 6 choose 6. Well, 6 minus 6 is 0. And we know that if this was a 0, then we're going to get 1. So 6 choose 6 is also 1. So the last thing we need to do is we need to multiply everything out and just get all written in a little bit more simpler form. So this would be 1 times a to the 6th times b to the 0, which b to the 0 is 1. So it'd just be a to the 6th power. That's our first term. All right, let me make sure I box that in so you can just see this term right here, right, is our a to the 6th right there. And we're just going to continue down the process. So plus, this would be what, 6 a to the 5th, b to the 1st, so b, plus 15 a to the 4th, b squared, plus 20 a cubed, b cubed, plus 15 a squared, b to the 4th, plus 6 a b to the 5th, and then the last one is 1 times a to the 0 times b to the 6th, so b to the 6th. So there's our a plus b to the 6th power. I'll expand it out. Okay, I'm gonna let you try b and just check it with the key. I'm gonna do part C now, just to kind of see it again, another problem. So remember, it's 4 choose 0 is the very first one. Y is our first part of that binomial, so it's gonna be in the first set of parentheses. And then this time we're gonna have a -2, since it's -2 in the other set of parentheses. Remember, this 0 always matches with the second set, right? Our second quantity, our -2. And then this one's going to be a 4 because those had to add to be 4. And we're just going to continue down the process now. So we have 4 choose 1, 2 sets of parentheses, y, -2. The -2 always matches. Sorry, this is a plus right here. I'm not sure why it really equals. -2 has a 1 on that exponent. And then the y is going to have a 3. We'll just continue down. 4 choose 2. So now it's going to be a y squared and a -2 squared. Now we're at 4 choose 3, which is going to be just a y and the -2 cubed, y to the first, right? Okay, and then 4 choose 4, which is going to be y to the 0, -2 to the 4th. Okay, so now we're just going to evaluate each one of those combinations. Well, 4 to the 0 is 1, right? 4 choose 0 is 1. 4 choose 1 would just be 4. 4 choose 2, that would be 4 times 3 over 2 times 1, which is 6. So 4 choose 2 would be 6. 4 choose 3 is the exact same thing as 4 choose 1. So we know that's going to be a 4. And then 4 choose 4 is going to be the same thing as 4 choose 0. So that's going to be a 1. So now we just need to kind of get all this stuff organized. So we have our 1 times y to the 4th times -2 to the 0, which is 1. And then we're going to have 4 times y to the 3rd times -2 to the 1st, which is -2. And then we're going to have 6 y squared Negative 2 squared is 4. We're going to add that to, well, 4 choose 3. Remember we told you that was 4 times y. Negative 2 cubed is negative 8. And the last one, 1, y to the 0 is also 1. Negative 2 to the 4th, it's going to be a positive 16. So, looks like our final answer here is 1 times y to the 4th times 1, which is y to the 4th. Then multiply all these out, so it'll be a minus 8y cubed plus the 24y squared minus 32y plus 16. And there's part C. All right, our final one, as far as I'm going to do in this section, and I'll let you do E by yourself, is 2x minus y to the 5th. So we would go with our combination. 5 choose 0. Then we're going to have 2 sets of parentheses, 2x and, in this case, negative y. 0, 5. We're just going to continue down the process. 5 choose 1. 2x to the 4th, negative y to the 1st. Now 5 choose 2. 2x to the 3rd and negative y to the 2nd. Remember, these always match. The 2 and the 2 always match. And these had to add to be 5. All right. See, we're at 5 choose 2, so now we're at 5 choose 3. We have 2x and negative y. This is a 3, that one's a 2. 5 choose 4. That's a 4, that's a 1. And then our last one, 5 choose 5. So 2x and negative y. So remember the 5's match, so that one has to be a 0 for the 2x. Let's see here, 5 choose 0 is 1. 5 choose 1 would be 5. 5 choose 2, well, that's 5 times 4, which is 20, divided by 2 factorial, which is 10. 5 choose 3, well, that's the exact same thing as 5 choose 2, so that's also going to be 10. 5 choose 4 is the same thing as 5 choose 1, so that's going to be 5. And then 5 choose 5 is 1, just like 5 choose 0 is. So we have 1, and then 2x to the 5th, well, that'd be 32x to the 5th. And then negative y to the 0 power is 1. All right, next one, we have 5. 2x to the 4th, well, that'd be 16x to the 4th. Negative y to the first power is still, it's going to be negative y. 5 choose 2 is 10. So that'd be 8x cubed. 2x cubed would be 8x cubed. Negative y squared is y squared. Okay, I bet I can fit these in here. 5 choose 3 is 10. That'd be 2x squared, so 4x squared. And then now we have negative y cubed. 5 choose 4 is 5. 2x to the first, it's positive now. Negative y to the 4th would just be y to the 4th. And our last one here, 5 choose 5 is 1. 2x to the 0 is 1. Negative y to the 5th is obviously negative y to the 5th still. So, final answer, after you multiply all those out, 1 times 32x to the 5th times 1 is 32x to the 5th, and we're just going to continue down this path. Right, there's our negative, so this looks like it's going to have a negative in front of it because it is a negative y. 5 times 16 times negative 1 is negative 80. X to the 4th y. There's positive 80, so we have an 80 again. X cubed y to the 2nd. Well, here's another minus. So 10 times 4 times negative 1 is negative 40. X squared y to the third. Ten x y to the fourth. And their last one minus y to the fifth when you multiply all those out. All right, so there's part D. So you've seen three different problems now with this binomial expansion. Each one kind of had its own unique aspect to it. Hopefully that gives you a good foundation to work with some of these problems. You saw I get a little bit faster. There's probably some things you don't have to do. You can skip some steps, but I'm hoping that you see that this is not as bad as it sounds at first, and you can kind of do these problems a little quicker as you get better and practice more. All right, example 4 is just kind of seeing if you can have the concept and apply it. So it says find the fifth term of this binomial expansion. The thing about it is you don't want to have to go through the whole process like we did in part D. So let's look for a pattern right here. You see how every one of these had, a similar approach. So first thing I'm going to say here is we had 1, 2, 3, 4, 5, 6 terms for our fifth degree polynomial. All right. The first term right here, we started, remember, with 5, choose 0. And then the second term was 5, choose 1. Third term had a 2 right here. Fourth term had a 3. Fifth term had a 4. And then the sixth term had a 5. So notice this number in the combination was always 1 less than the term number we're working with. So if we're trying to find, let's look at example 4 again. If we're trying to find the fifth term, that means the bottom portion of our combination is going to be 1 less than 5. So it's going to be a 4. So you can see again, here's our first term we're working with. If I try to find the first term, that would be a 0 in the bottom of the combination. So our 8 is our exponent. So we know it's going to be an 8, obviously, for the combination portion of our fifth term. And I don't really care about all the terms before and after. I just want to focus on the fifth. So remember, this number right here is not going to be a 5. It's going to be 1 less than 5. 4. So 8, choose 4. This would be helping us with that coefficient on the fifth term of our expansion. So then we just have these two sets of parentheses. We have A and 2B. So I'll write those in there. And it's just a matter of filling out what their exponents are going to be. Or remember, this number right here always matches this number right here for the binomial theorem. So if that's a 4, this one also has to be a 4. Okay, so those match. And then this position, these have to sum, they have to add to give us an 8. So it's also going to be a 4 in this particular example. So it says find the fifth term, so it's just a matter of working this all out. So 8, choose 4, remember that'd be 8 times 7 times 6 times 5, all over 4 factorial. Okay, and then we're going to have a to the fourth. I'm going to write that in there. Let's just go and do this one too. 2 to the fourth is 16, and b to the fourth. All right, well, I would say, 4 and 2 is 8. 3 and 6 would simplify to become a 2. So it looks like it's 7 times 5 is 30. 35. 7 times 5 is 35. Times 2 would be 70. All right, and then we're saying times a to the fourth times 16b to the fourth. So 70 times 16 is 1,120. A to the fourth, b to the fourth. And if you use a calculator here, that's fine. I'm fine with you just, multiplying all these out with the 16 and get you don't have to do that step if you don't want to. But there's our fifth term of our a plus 2b to the 8th expansion. Okay, last example. Find the coefficient of the term a to the 4th, b to the 7th in the expansion of this nasty thing right here. So the only thing we're looking for is a coefficient. We don't have to even find the term in this particular example. So example 4 is find the whole term. This is just looking for the coefficient. A little bit different thought process because of the information that's given to us, but we know we have an 11. So we can go and set our combination to have an 11. And then we know our two parentheses here are going to be a 2a and a negative 3b. So put those in. All right. Sloppy b, sorry. So now, a to the 4th and b to the 7th. Well, if we're looking at this, there's nothing that's going to cause anything to change on the a and the b as far as their exponents are concerned. So the only way we can get a to the 4th and b to the 7th is if the exponent right here on the 2a parentheses is a 4, and then likewise on the negative 3b, if there was a 7 on that exponent. And remember, this one has to match this one in our combination. So if that's 7 on the second parentheses as an exponent of 7, then our combination is going to have a 7 right there. So the only thing we're concerned with here now is just figuring out the coefficient. So remember, 11 choose 7 is the same thing as 11 choose 4. I'll just go ahead and write all that real quick. Well, 11 choose 4, remember, is 11 times 10 times 9 times 8. So I'm going to do 11 choose 4 just because it's simpler. Sorry, I'm not sure why this is not focusing in. So 11 times 10 times 9 times 8 over 4 factorial. 4 times 3 times 2 times 1. Well, the 4 and the 2, we'll take the 8 out. 3 and the 9 would be 3. We saw that earlier. That's 330. So it's going to be 330. And then we still have 2a to the 4th, negative 3b to the 7th. If you wanted to use a calculator here, I'd be perfectly fine with it because I think this number's pretty big. So 330 times, well, 2 to the 4th is 16, and then times whatever negative 3 to the 7th power is. So let me just kind of punch it in my calculator over here. Looks like it's going to be negative, obviously, because this is a negative. So negative 11,547,360 is everything as far as the number's concerned. And then we'd have a to the 4th to b to the 7th. Remember, the question said, what's the coefficient? That's all we're concerned about. So there it is. Negative 11,547,360. Sorry, I'm not sure why I didn't focus in here at the very end, but hopefully I was able to give you some a good base. Then the notes, obviously look at the key if you have on some of those problems that I said, work on your own. But as always, let me know if you have questions. You guys are doing a great job. Stay out of the trees.